And I'm going to share my screen. And I'm looking at the truss module. And before we get started on trusses, I did a lot of grading last night of some of the quizzes, and I wanted to show you guys something. So take a look up here under class notes. It says solving systems of equations, and I'm going to open that up. And let me move my pictures of you guys and open it up full screen. And I don't have any free body diagrams here drawn, but I wanted you guys to take a look at this. This is just a sample of what somebody did. So they must have had 2 free body diagrams. Well, I don't need to read it to you. Why don't you just take a look? Let me give you a couple of minutes. Okay, so we read from top to bottom and left to right, right? So I start with this and I say, oh, for free body diagram number 1, the person did sum of the forces in the Y, and they solved for, they brought the weight onto the other side, and then they solved for CY, and then they plugged in AY, and I'm like, where the hell did they find AY? So I look above, trying to find AY, I can't find the calculation, and then I look below and I say, oh, they went to free body diagram number 2, they did sum of the moments about N, they found AY, and they took AY and then came back and plugged it in here. Actually, they plugged in the wrong number, it looks like. Okay, then I go to this one and I say, okay, they did sum of the forces in the X, they got CX in terms of T, and then they plugged in a value for T. Where the hell did they get the T? It's not above, but oh, they got it here. So I want to just present to you that this is one reason why it's better to solve the moment diagrams that have one unknown first. Because once you find AY, then when you do this, you could plug in AY. There's nothing on here that shows that they took this AY and plugged it in here, and they took this T and plugged it in here. All right, so I see they did make a mistake. They should have plugged 81.5, and by accident, they put 62.5. But the point is that I read from left to right and top to bottom. When you find something on the bottom and then you bring it back up to the top, it's very confusing. For a peer, an engineer, another friend to look at it, or your boss. So you really want to, if you want to set it up like this, then you have to say how you got the AY, like maybe draw an arrow and say, oh, I plugged it in here, or T, I plugged it in here. But the better thing to do would be to solve the moment equation and solve for the unknown, and then do the sum of the forces in the X and the Y so you could start plugging numbers in. Does everybody see that? Give me a nod or something. Okay, so I'm going to get out of this now. I'm going back to course. Any questions on that? Okay, so I'm going back to the course module now, and I'm looking at the overview of trusses, and I'm just pulling it up here because I already opened it. So in this module, you learn how to solve for the forces in members of truss. So let's just review what we did on Monday. By the end of this module, you will. All members in a truss are a 2-force member, and their internal forces act along the axis of the member. We already know that from frames. Remember, the difference between frames and trusses is frames has at least one 3-force member. Excuse me. So as long as you see a 3-force member, you know it's a frame and not a truss. But if it's all 2-force members, it's trusses. Okay, then we also learned on Tuesday that there's something called 0-force members. 0-force members are members that have no force. And there were 2 rules to determine which members are 0-force members. Rule 2 we looked at first. You look at a joint, And in both rules, you look at a joint and you look at how many members are coming together. For rule 2, if a joint has 3 members connecting at the joint and 2 of the members are collinear and the third one is not collinear, the member that is not collinear is 0, and the 2 collinear are equal and opposite forces. Rule 1, we look at a joint that has 2 members only. They're connected at the joint and there's no external force or connection at the joint, and both of those members are 0 force members. Okay? Then towards the end of class, I mentioned that there are 2 ways to solve for the members of trusses. One is called method of sections, and one is called method of joints. We haven't looked at method of joints yet. But notice in either method, the first thing you do is you determine which members are 0 force members. Then the second step in both is you separate the whole structures from its main supports and determine the reactions at the main supports. And then for methods of sections, we have 3, 4, and 5 steps. Step 3, break the truss at the members whose forces are unknown and they're in question. You draw a free body diagram of the section. Maybe that's what I should say. Draw a free body diagram of one of the sections. Could I say that?
Relevant section?
Yeah. Actually, either one is fine. One might just take a little bit more work. I'm going to just call it a section because it's called method of sections. So break the truss. Okay. Draw a free body diagram of one section. I mean, it could be left, right, top, bottom. And then using the equilibrium equations, determine the forces in those members. I'm going to save it. Okay, I'm going back to the module now. And now I'm going to the truss class problems. And you guys, shortly, I'm going to turn to my paper. So you're going to need to pull up the class problem. It may still show up on the screen. I'm not sure. We'll see. Okay, so I'm going to the class problems. And there are 2 problems. This one, we're going to skip this one because this is going to be method of joints. But we're going to do this one instead. And we already talked about it. So, okay, here are the names. I don't know where we ended last time, so I'm just going to start in the middle. Jordan, you here?
Yes.
Okay, Jordan. So this problem, a truss problem, asks us to find these 4 members. Okay. And what's the first step in a method of sections? What do we do? Cool hair, Jordan.
Thank you.
Yeah.
Method of sections, would we look for the 0 force members?
Yes. So they only want us to know about these 3. So are any of these, sorry, these 4, are any of these 4 0 force members?
No.
Try again. Do you see any joints that satisfy rule 1 or 2?
I guess CG would.
Okay, so which joint are you looking at for determining rule 2?
G.
G. So you look at G, there's 3 members there, 2 collinear, 1 non, no external support, no external loads. Yes, CG is equal to 0. So we already canceled out one thing really quickly. Okay, now we're going to look, Jordan, Laura, the next 3 forces they want us to find is CD, CF, and FG, right? But what's rule 2 of sections say?
To draw a free body diagram around the area that you want to determine.
Go look at their rule. Rule number 2 says, let's just look.
Yeah, to break the truss at the members whose forces are asked for.
No, number 2, rule number 2.
Oh, okay. Oh, I had the other one. Separate the whole structure from its main supports and determine the reactions at the main supports.
Okay, so number one was finding zero force members. We did. CG was equal to 0, looking at joint G. Rule 2, separate the whole truss from its main supports and find what, so Laura, what kind of connection is at A?
It's a joint.
What kind of joint is it? What kind of connection? What kind of support?
I don't know the name of it.
Okay, yes, you do. Look at this one. What's at F?
A roller.
Right, what's at A?
Fixed.
No, if it was fixed, it would be totally glued or welded to the ground or to the wall. It's a pin.
A pin.
Most common are pins. So what does a pin resist, Laura?
X and Y.
Okay, so we're gonna have an AX and an AY, right? And what does a roller resist?
Just in the Y direction, so the normal.
Right, so let's just call it, we could call it FY, we could call it normal. Okay, so we have on my scrap, if I were able to draw on here, I would draw an AX and an AY, I would draw them positive, and I would draw this normal here positive, right? Let's call it FY because there are times now that the force might be in the other direction on these connections.
Okay.
All right, so let's call it an FY. So give me an equation that I could find one of them.
The sum of the forces in the X.
Great, sum of the forces in the X, and you sound very confident on that. And what did you get?
0, AX 0.
AX is equal to 0. Okay, so Laura, Liam. So we just found AX, we still have AY, and we still have FY. What's the next equation you want to do?
The moment about A.
Great, and what would you find?
FY.
Right.
The normal.
Good, and then what equation you want to do next?
The sum of the forces in the Y direction.
And what would you find?
AY.
AY, okay, and Luis, you here? Mackenzie? Marcine?
Yes.
Okay, so we solved for AX, we solved for AY, and we solved for FY, and we found all three of them. What's another equation we could do to check it? Because we're gonna do an awful lot of work. Let's check it at the beginning to make sure. What do you wanna do? What?
It's for a check. We could do a moment about a point.
Great, we could do a moment about a point. Okay, so now, okay, so Marcine, now Maria. So actually, I don't know if you guys already calculated them, but sum of the forces in the X equals 0 leads to AX equals 0, as Laura said. Sum of the moments about A equals 0 led to FY being 5,000 pounds. And sum of the forces in the Y equals 0 led to AY equal to 1,000 pounds. And then I did a check and it turned out. So AX is 0. Let's not do the math because you know how to do that. And I've seen your quizzes, you know how to do that. So AX was 0, FY was 5,000, and AY was 1,000. Okay, we're up to, Maria, did I call you already?
No, I mean,
But
you did,
okay.
and
I called you, but I didn't give you a question. So
Yeah.
step 1 was to find the 0 force members. Step 2 was to take the whole structure away from its main supports and find the reactions at the supports. What's step 3 for the method of sections?
You have to break it up so that CD, CF, and FG are external forces.
Great. So I break it up right here. And how many unknowns would that give us, Maria?
3.
It would give us 3 unknowns. You're sure of yourself, right? 3 unknowns. And it's a 2D problem. So can I find all 3 of them?
Yes.
I can. So now, Maria, you get to decide if you want to do the left side or you want to do the right side. It doesn't matter.
I want to do the right side.
You want to do the right side. Okay, so let's all draw the free body diagram on the right side. And now I'm going to turn to my, I'm now going to, I'm now going to be the host on my camera. So I'm swapping while you're doing that. I'm going to stop sharing. Yay. Okay.
Got it.
Okay. So Maria said she wants to do the right side of the problem, right? So let's draw the right side. And I draw everything away in tension, right? If I'm drawing everything away, it's tension. So this is what? CD. This is CF. And you could call it FC, whatever you call it. I guess maybe I should call them from where they're coming from. So DC, FC, FG. And I have some dimensions here. This is 6 feet. I have 1,000 pounds here. At D, I have 2,000 pounds. Some of you may have already figured this out. And here we have FY, which is 5,000 pounds.
Joanne, is it usually convention to draw the broken trusses as tension instead of compression?
Yes. Yes, you could draw them any way you want, but it's standard to draw them away in tension. So then we're consistent, meaning if we get a positive value, then it's tension. And if we get a negative value, then it's compression. Okay. Could somebody speak again?
Yes.
Okay. Thanks. Okay, so Maria, we wanted to draw the right side. So now we have 3 unknowns, right? Give me an equation to solve for one of them.
Some of the forces in the Y.
Great.
In the Y.
Now, remember, I hear an echo from me and it's horrible. I'm going to try to ignore it. Typically in statics problems, we find all the components first and do checks. In trusses, there's going to be a zillion things you need to find components of. So I just jump ahead and I don't find components. I just solve them in the equilibrium equations, which I see Matthew smiling. I think he is appreciating that, being a PLC physics tutor where they don't make them do checks. They're horrible people over there in physics, but I'm becoming horrible now. Okay, so we have Fy, 5,000 minus 2,000 minus 1,000 plus, look at this FC. I don't have directions on it. So let's see, it goes 8 up and 6 across. Well, I'm not going to do 6, I'm going to do 3, 4. It's a 3, 4, 5 triangle, right? You guys, is this too small? Should I zoom in closer? This distance here is 6. This distance here is 8. So I could write 6 and 8, but I'd rather just do 3.5. So in the Y direction, it's 4/5 FC equals 0, and I could find FC, and it turns out I did the math already.
So you kind of did similar triangles for this, like mentally?
No, not similar triangles. I'm doing using ratios. Let's just erase this again. Here's a force. I have to show the direction. We're not given angles, so we do not solve for angles. We're given distances. The distance going from F to C up here is in the X, it's 6. So I could say 6. Oh, I see what you're saying. Yes, you could say it's similar triangles, or for me, I'm just taking the 6 and 8 and dividing it by 2. So this is 3, and this is 4, and this is 5. But yeah, Angel, you're right. It's similar triangles, but I'm just
Cool.
dividing by the same factor. I think that it's called a factor.
Yeah, definitely. All right.
Okay,
Thank you.
FC comes out to be negative 250, 2,500. So Maria, is this in tension or compression?
It's in compression.
Right, so you put a big old C in to the end of it. You have to, on truss problems, you
Joanne, can you
have
scoot the
to
paper over to the
report
right?
whether it's tension or compression. If we got a positive, it would be tension because we set it up. We drew it initially as tension. We drew it as tension. If we got a positive, we would have put a big old T here. But because we got a negative, it's compression. Jason, you asked a question?
Yeah, can you scoot the paper over a scotch to the right?
Yes.
Thank you. Ah, there it is.
But never flip the arrow. That's our rule. Is even
Never
if we drew
flip
it that
the
way, we
arrow.
never flip the. Okay.
You'll make mistakes. Okay, Maria, you did that one. So I'm going to Matthew. What's an equation you want to do to find another one? Matthew?
Yeah, I'm here.
Sorry.
Let's do the sum of the moments about point D.
D. Can we make it easier?
It seemed pretty easy to me because we just have the
We'll have
force
two
at E and the
unknowns, right? But we
oh,
solve
because we
for
have FC. That's right. Okay.
Let's do
But
something easier.
Well,
do
the
F
vertical, the vertical
Yeah.
one cancels out.
The vertical one, but we still have the X. I
Hmm.
guess we can do it, but let's do this one. It's easier. Sum of the moments about F. So it's DC times 8 positive, 1,000 times 6 negative, and 5,000. Nope. See, it's a lot less work. So DC turns out to be, what did I get for DC? 750. Matthew, it's positive. So tension or compression? Keep unmuted.
tension.
Thank you. Okay. Myra, what equation do you want to do now?
Some of the forces in the X.
Yes. Then we would have one unknown. What about some of the forces in the Y? I mean, they're about the same, but if I do some of the forces in the X, I have to remember to substitute these values, right?
Isn't the Y already done though?
Oh yeah, you're right. Sorry. Okay, minus FG minus DC minus 3/5 of FC equals 0. And FG turns out to be 750. Myra, I got a positive. Tension or compression?
Tension.
Tension. And then Myra, if I wanted to check these values, what could we do? What other equation could we do?
Some of the moments about another point.
Yeah, some of the moments. So a check could be some of the moments about some other point. Okay, and I've already checked it, so it's right. Okay, so let's start from the beginning.
I have a question, Joanne.
Yeah. Let's do the summary first, and then you could ask.
Okay.
So the first thing we did is we looked to see if there were any zero force members, right? And we determined that CG is equal to 0. And it's, or just say, you could just write rule 2. Okay, so you have to write that because one of the questions to find in the problem is what is CG? So GG is 0 from rule 2. So first thing we did is 0 force members. The second thing is we did the whole free body diagram and we found the reactions at the supports. And then we decided where we were going to cut the section and we drew a free body diagram of the section. And then we did the equilibrium equations to find those unknowns. Okay, Dave, question.
I just want to make sure I understand the logic here. On your sum of the forces in X, you actually put negative. You put minus 3/5 FC, but we know that it's backwards. So you just had to say negative and then also put in the negative. Is that right?
Yeah, let's. Yeah, it's a good idea. I should probably have done the whole work.
Because that has tripped me up a couple times on quizzes.
Yeah,
where like it's flipped and flipped again, and I just want to make sure we follow.
So
it
it's
right.
negative FG minus whatever DC we got here, which is 750, minus 3/5, and then whatever's here, we have to bring it down, negative 250. I'm glad you're asking me this question. And then FG turned out to be 750 plus, and it's a tension. So you guys, this is great. You have to put in the negative if you got a negative.
Okay, thanks.
Think about it, because when we do sum of the forces in the X, from our free body diagram, we have the X component of FC going in the negative. But the value for FC we determined is actually in the other direction. So we have to put in this next negative. Because if we flipped this due to this negative, it would be a positive X. Thanks for bringing that up, Dave.
I have a question.
Yeah, Jack.
If we had wanted to do a moment about C to find FG.
Yes, let's do it.
That would work too, right?
Let's do a check. So remember, I said this at the end of last class. Let's do a check and say moment about C. Now, C is a virtual point, right? It's a point over here. But DC goes through it, FC goes through it. So when we do the sum of the moments about C, we have FG times 8 negative. We have 2,000 times, what's this distance? 6. 6 feet. No, I'm not going to put the feet. 6 negative. 1,000 times 12 negative. And then plus, then F, I jumped ahead. FY up, which is 5,000. 5,000 times 6 positive equals 0. Did I get them all? So CFG creates a moment, DC and FC does not. And at C, there is a force. What is it? 2,000. But that doesn't create a moment because it's at the point. So it's only FG, D, E, and FY. And FG would again should turn out to be 750 pounds positive with a T. There are many times that you'll use a virtual point because you want to make this the easiest you can, the least amount of work. And Maria, I'm thinking that maybe you picked the right side. See, this is where the ones we had to find. and maybe you pick the right side because it's smaller. You know, I don't know. There's two external, there's a reaction at the support. Well, the left would have had two external and one reaction at the support. So it's the same, but the right side is quicker to draw because there's less members. But you could do the left or the right because remember, it's equal or opposite. You guys look at this. Doing the right side, I drew CD to the left. Had I done the left side, I would have drawn CD to the right because it's tension. Tension, 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 tension. So I want to show you why it's tension. Is everybody with me? If you took a pen and you wanted to apply a tension force, how would you pull it? I just told you. You pull it. You would pull it like this. Can you see me? You can see my face, right? Okay, look at this. Here is a member. Here's my pen. In order to apply tension, I am applying an external load. Let's just call it T. I'm applying an external load of T, right? Does that make sense? Here's my pen. Well, what is the pen experiencing? Inside the pen, tension is like this.
I don't follow that.
Okay. Okay. This is comfortable, right? With my hand, I am taking the end of the pen and I'm pulling it away. On the external of the pen, I'm applying a tension force that pulls it apart. In static equilibrium, this pen is trying to resist the tension so it doesn't break. So here's the tension on the outside. Here's the tension on the outside. What the pen is experiencing is equal and opposite. This inside is what tension is experiencing. And this drawing is the same as what we would draw. If I have a body over here that's connected to the ceiling with a cable, when I draw the body, I draw the tension going away. This is tension. Here, tension's away from the body. Tension away from the body. But what we're seeing inside, tension inside is pushing towards it. So, like, look at this. When I draw a free body diagram,
it's kind of like if we pull on the pen, what holds the pen together?
You guys, I want to talk. And then Matthew, you could talk. Here's the truss, and we're applying a tension of CD. We're applying a tension. It's going from D to C. I'm applying an FC and I'm applying an FG. This is the body that I'm analyzing, right? And here, these are drawn away, but look, it's really drawn like this. This right here is C and this is D. Okay. So when we're drawing a free body diagram of this and we draw it away, it's tension. But when I look at the inside of the body, look, it looks the other way. The reason that I'm even going down this rabbit hole is because when students see this, they think that's compression, and that is not compression. One more thing, and then Matthew, you could talk. Let me get another piece of paper.
It was Isaac, not Matthew.
Oh, Isaac. Okay. So here's my body. This is tension drawn away. What it experiences inside is this. This looks like compression, but it's not. When I have a body where you're actually applying compression inside, it's experiencing this. So this is compression. This is tension. And maybe you didn't even have a question about it yet, but when you start to do your homework, at some point, somebody is going to look at this and say, isn't that compression? But it's not. It's only if it's compressed from the outside that it's compression. Okay, Isaac. What did you want to say?
I was just processing out loud and trying to see if what I was saying was correct. It's not important. No, it's not. It's you said everything I was thinking.
Anybody else? Matthew, do you have a way of describing? Well, actually, you guys never do tension and compression in physics. I don't think. All right. So basically, wait, hang on a sec. So methodically, we draw the forces away as tension. If you get a positive value, it's tension. If you get a negative value, it's compression. And whatever value you get, positive or negative, is what you have to substitute in the problem. So here we had to for FC, we had to substitute in the negative 2,500. Okay, I'm going to keep going. Well, I'll wait a little bit, see if there's any questions.
Actually, Joanne, I had
Remind me at
question.
the end to come back to this. Yeah, Matthew.
When we went to like that virtual moment about point C, I guess I was just it seemed a little odd that we were neglecting the left side of that point, where the rest of that
You
point
mean
is
this
attached
whole
to.
left section?
Yeah, well,
yeah, the whole left section, right?
Yeah, specifically the two members that are attached to point C on that side.
You mean the ones that are attached on the left side of it?
Yeah.
Okay. Okay. So these problems were all in static equilibrium. When we break it right here, this whole left side is in static equilibrium and the whole right side is in static equilibrium. Maria chose for us that we're only going to look at the right side. The only point, when I pick a point, I'm trying to find a moment about, I could have picked point A if I wanted. And I could totally ignore all this because I'm only looking at static equilibrium for the right side. So right now, there are 1, 2, 3, 4, 5, 6 members that are in static equilibrium. And when I choose point C, I'm still only choosing that point for this that's in static equilibrium. So I'm not going to throw in another member. But had I looked at, if I broke it here and I did point C, I would have had to look at these two. These guys are still connected. And when they're connected, When they're connected, it's all internal, not external. So Matthew, you could have actually asked, when I did the sum of the moments about C, why didn't I include member DE? But it's because the forces in DE is all internal to the system. I'm only looking at the 6 external forces. Does that help?
Yeah, I think so.
All right, maybe think about it more.
Mm-hmm.
Okay, so could you guys remind me to talk at the end about if there was a weight? I want to come back to this problem, okay? So now what we're doing is we're going to this problem, and I could zoom in. But we're going to do method of joints. So the problem asks, determine the forces in all the members. Luckily, there are only, my name sheet just fell somewhere. Who's after Matthew? Oh, here it is. Matthew, Myra, we did Miles. Miles, you here? Okay, Peter?
Yes.
Okay, Peter, looking at the overview, what was the first step in method of joints?
We need to determine the zero force members.
Correct. Are there any zero force members in this? Does any joint follow the rules of rule 1 or 2 for zero force members?
No.
No. So there's no zero force members. Okay, what's the second step? What's the second step of the method of sections? It's the same. Step 1 and step 2 are the same for both.
Oh, sorry, I was muted. We need to separate the structure from the main supports.
Correct.
And determine the reactions.
Great. Nope, that wasn't a very good picture. And Peter, what's at A?
There's a pin at A.
So what do I need to draw?
AX and AY.
Great. AY, AX. What's at C?
Also a pin.
Take a look closer.
Oh,
can you see the picture?
Yeah, the oh,
it's a roller.
Yeah, sorry. A little
so what's the force?
CX and CY, and then
a roller only has a Y.
Oh, okay.
So it's only CY. Okay, I'm going to give you the distances because that's going to take a bunch of geometry and we don't want to deal with that. So this is 8. This is 4.5 feet. And this is 6 feet. Can everybody see my drawing? So 8 feet, 4.5, 6. So Tim, what equation do you want to do first?
We could do sum of the forces in the X.
Sum of the forces in the X equals 0. And what is equal to 0?
Well, we have the 1,200 pound force.
Oh, right. Sorry.
Well.
Whoa, boy. Look at that. AX plus 1,200 equals 0. AX equals negative 1,200 pounds.
Yes.
Good job. Okay, let me find the problem. Here it is.
Joanne, there's a force missing at point D.
Did I forget something? Thank you.
Yeah.
a downward force of 1600, I believe.
Thank you, Angel.
Yeah.
Okay, Tony, what next for? What other equation do you want to do?
We could probably do some of the moments at A, so we could solve for CY.
Great. And CY turns out to be 1152 pounds. Tony, you want to keep going? What's the next equation you want to do?
We could just do some of the forces in Y.
Equals 0. And what happens is AY turns out to be 448 pounds. And then let's do a check. Tony, give me an equation.
I don't know. You can do some of the moments at C.
Great. And we'll check it.
Cool.
Okay. First step, are there any zero force members? And there were none. Second step, take the whole structure away from its main supports and find the reactions at the supports, which we did. Okay, what does it say? We're up to Victoria. Victoria, what is the third step for method of joints?
The third step is using statics of particles at each point to determine the forces of all members.
Okay. Does it say statics of particles at each joint?
Yes.
Okay, great. Okay, so you guys, on this problem with sections, were we doing statics of particles? Or Victoria, here, were we doing statics of particles or statics of rigid bodies? Victoria.
Statics of rigid bodies.
Why? Well, how did you come up with that?
It was a guess.
Okay, so take a look at it. When we do a free body diagram of a particle, all the forces are concurrent, right? They're all being applied at the same point. But in statics of rigid bodies, forces are being applied at different points along the body, and we have to do some of the moments, right? Victoria?
Yes.
Yes. So this is a rigid body because all the forces applied at different points along the body, and we wound up doing some of the moments. But for joints, they are telling us to do statics of particles. Why? Because we're looking at each joint. So everybody look at this for a minute. Everybody looking up here?
Yep.
They're asking us to find every single force. They're asking us to find a force in every single member. We have to find this and this and this and this and this. And if we want, we can say we're doing method of sections and cut it right here. But what we're actually doing is we're doing method of joints. At A, we learned that AY was 448 pounds. And now if you want to draw AX the other way to have a positive, you can, because you're going to be drawing a bunch of free body diagrams. So do we want to draw it the other way? We got a 1200, but we got a negative. So I'm drawing it in the negative direction with a positive. And then I have AB and I have AD. And notice I'm drawing them all away because I'm drawing them as if they're in tension. So this is a joint. Does everybody see that? Here's my point A. I drew my 1200 in the negative direction and put a positive. And then I drew AB, AD way, and 448. So first, am I confusing you? Because initially we drew AX in the positive direction and we got a negative value. So I decided to just draw it in the negative direction with 1200. Is this okay with you all, or is that confusing? If it's confusing, we would just draw the 1200 here, but we have to put a negative. So what would you prefer to do?
Draw it how you had it.
Okay.
I think it doesn't matter so long as we like whatever we pick at the beginning, we just stick with it.
Okay.
It's the balance is like, do I want less negatives or do I want to stick with the convention of always drawing my unknowns in the positive direction, whatever's less confusing, but it's a give and take.
So you choose. See, with method of sections, I like method of sections because you draw one free body diagram of the whole structure, find the supports. Then you draw one more free body diagram and you're done. With method of joints, you have to draw a free body diagram of every single joint. So because I'm drawing so many free body diagrams, I rather change the convention. Okay.
Do we need to draw every single joint, or could we? It looks like if we just look at joints B and D, we can get every single member here.
No, we can't. That's a good question, Angel. But look, we are now back to statics of particles. What equations do we have for statics of particles?
Sum of the force in the X and the Y. No moment.
Right. So I only have two equations for each joint.
That's a lot.
Here, there are three unknowns. I can't jump to that and do it. I could only do joints that have two unknowns first.
Okay, that makes sense.
All right. So that's why you know that with trusses, you're doing method of particles for the joints, but you're doing you're doing statics of particles for joints, and you're doing statics of rigid bodies for sections. Okay, so Victoria, we're up to Mani. Yep. Mani, you here?
Yeah.
Okay, so we have joint A. What equation do you want to do first?
The sum of the forces in the X.
How many unknowns will I have in that equation?
You're going to have two.
So we don't want to do it.
Okay, the sum of the forces in the Y will have only one.
Right. So sum of the forces in the Y is 448 plus 4/5 of AB equals 0. And AB turns out to be 560 negative pounds. So Amani, once I calculate the number with a positive or negative, what do I have to put here?
Tension or compression.
Right. And which one is it?
Compression.
Compression. Okay. Then we could do sum of the forces in the X. So it's negative 1200 plus AD plus 3/5 of AB equals 0. And AD turned out to be 1536 pounds, and it's positive. So Amani, what is it?
Tension.
Tension. So remember, you guys, we're starting to do with these, with trusses, we're using ratios all the time. Why? When you buy beams, you're buying a length of beam, right? Here's a beam. This beam is 8 feet long. This one's 4.5. This one's whatever. What was it? 6 6. This beam, I'd have to figure it out. So let's see if it's 6, 6, 8, this has got to be 12. I'm buying a 12-foot beam. This one is 4.5 squared plus 6 squared is whatever squared, whatever it turns out to be. To me as an engineer, the lengths are important. I don't give a shit what these angles are. I'm not going to report them. So you're using ratios all the time. So take a look at this, you guys. You got to remind yourself. 3, 4, 5. If I want the X component, I got to use the 3 over the 5. If I want the Y component, I'm using the 4 over the 5. You knew that already, but just you're going to be doing it so much now. Okay, so now, Angel, what joint do you want to do now?
I'm thinking joint C.
Look closer. There's one that's way easier.
Is it D?
Yeah.
All right, then I guess I'd want to do joint D.
Okay, and you know what? Can we not even join it? I mean, draw it. Let's not draw it.
For sure, we have it there.
Okay, but we'll draw it. Okay. For D, we have AD going that way because we always draw them in tension. This is DC, this is DB, and this one is 1600. What is DB going to be equal to, Angel?
That's a 0 member, isn't it?
No, we found no 0 members because joint D has a 1600 at it.
Oh, yeah, you're right.
What's DB equal to? Look at the picture. Look at my picture.
Oh, it should just be equal to 1600.
Right. Tension or compression?
And that is positive, so it is tension.
Right. And how did you determine the DB? What did you do in your head? Which equation?
Well, in my head, I did the sum of the forces in the y direction.
Great.
So that got me DB minus 1600.
Okay. So let's do the sum of the forces in the X in our head. Sure. What is DC going to be equal to?
AD.
AD. And what did you get for AD? A positive 1536 pounds. So is it up? Wait. This is what I usually do, so I don't have to rewrite stuff. Here, hang on. DC equals AD, which equals 1536 pounds, which equals, DC was the one I was trying to find out. DC, and I put a box now like that. Tension or compression, Angel?
That is a positive value, so it is tension.
Tension. Okay, Bond, what do you want to do next?
It looks like the only point left is B.
Well, there's B and C still, right?
Oh, yeah, there's C.
Okay, but is one of them easier than the other?
I think B would be easier because there's the 1200 pounds that's on it.
Okay, so at B, here, at B, we know 1200. We also know AB now. We also know BD now, but we're still trying to find BC, right?
Right.
So there's only one unknown. And what equation are you going to do?
Well, it looks like we can do sum of the forces of X or Y.
Correct. Great. We could do either one. Let's look at C. At C, we have BC, which we still don't know, but we know CD, and we know that this force here is, we solve for it. So I would say C is less work because there's only 3 forces here, where here there's 4. I do C.
I see.
So joint C. Okay. CY was 1152 pounds. CD is equal to DC, which equals 1536 pounds. Oh, I should write it here. And then we have CB, and we have to put the direction of it. And we should also have an X and Y axis, which I didn't draw yet. And Bon, what's the distance in the X for CB?
It's, I would say -4.
Okay, yeah, but it's a 4, 3,
And a
4,
3.
5 triangle, right?
Right.
Okay, and Bon, how many unknowns are here?
Well, it's just the CB.
It's only one unknown. So which equation did you want to do?
I guess some of the forces in the Y.
Okay, so it's 3/5 CB plus 1152 equals 0, and CB turns out to be 1920 negative.
And that makes it a compression.
Right.
Can you move the paper up a little bit?
Yeah. Comes out to be compression. Bon, can we do a check? We found everything now, but let's do a check.
Yeah, we can take a moment at any point. Or are we checking the whole system of A, B, and...
Oh, I see what you're saying. No. So we can't take a moment because they're all internal forces, right? So let's just stick with the joint we're at with C and do a check it with for C, CB.
Okay.
So what could I do?
You can do the sum of the forces in the X.
Right. So negative 1536 minus 4/5 of CB equals 0. Negative 1536 minus 4/5 of negative 1920 equals 0. And it checks. We should check it. Four-fifths of 1920. Yep, checks. Okay. I wanted to share my screen. But that means you're not going to visually see it on a tape. But that's all right. That's the way we're going to deal with it. Okay, so I'm sharing my screen with the problem. Okay, can everybody see my screen? You guys?
Yeah.
Yep.
Okay, and I have my paper here too. So for both method of sections and method of joints, the first thing to do is to find the zero force members. Second thing you do, you take the whole structure away from its main supports and find the unknowns, the reactions at the supports. Now, with this method of sections, since we're only going to analyze the left side or the right side, when I take the whole structure, I really only need to find the reactions at the supports on the left or the right. Does everybody see that? So if I had two pins here, let's see. Colin. Colin? All right, Daniel C.
Wait, I'm here. Sorry.
Okay, Colin. So if, let's say A is a pin and F is a pin, that would be two reactions at each support, which is a total of 4 unknowns. We wouldn't be able to solve it by just looking at the total structure, but hopefully we could find the reactions at one of the supports, because when we do method of sections, we're only looking at the left or the right side. So when Maria said, let's analyze the right side, you would need to know what F is, the reactions at F. You wouldn't have to know the reactions at A. So when you take the whole structure away from the supports, if you're going to do method of sections, you only need the supports on one side. But if you're doing method of joints, where they're asking us for every single force in each member, you need to get the reactions at all the supports. Okay? So for both, you get the 0 force members, you take the whole structure away from the main supports, and then you determine whether you're going to do method of sections or method of joints. This truss I picked is small. There are only 5 members and there are only 4 joints. It wasn't that intense. But imagine doing this problem with method of joints. 1, 2, 3, 4, 5, 6, 7, possibly 8 free body diagrams you would need. So you could see why I like method of sections better. In the real world in engineering, you plug the truss into the computer, into a truss program, and you put in all the external supports and you put in the external reactions, and the computer program solves for all the forces in each member. So it's important that you know how to do method of joints, but you're going to ultimately use a computer program to calculate it. Okay, but now I want to talk, well, let me see. Does anybody have a question? Colin, you have a question?
I don't.
Oh, okay. Okay, I'm going to go back to sharing my screen. I'm back to this problem. So this problem initially said, each member is made of timber having a weight per unit length of 6. There's a 6 right here, pounds per foot. So each member is made of timber and it has a weight per length of 6 pounds per foot. It says, assume that the weight of each member can be represented as a vertical force, half of which is applied at each end of the member. So I'm going to now stop sharing the screen, and instead I'm going to use my paper. So we have this truss. It's let's zoom in a little. Okay, so this is A, B, C, D, E, F, G, H. So they said that the weight of each member is equal to 6 pounds per foot. That's a distributed load, isn't it? That's like saying this. Does everybody agree? Well, let's look at the distances. This is 6 feet, 6 feet, 6 feet, 6 feet. You guys, you don't have to write this down, okay? But I just want you to understand it. I'm not going to give you a problem like this, but this is a real world problem. So I'm erasing the distributed load. If it is 6 pounds per foot, Daniel C. Daniel H. Danny.
Yes.
Danny, oh no, whatever. Danny.
Yeah.
From A to B, it's 6 foot long. So what's the weight of the piece of wood here from A to B?
What's the weight?
So it's like a distributed load.
Right.
6 pounds per foot. So if it's 6 feet long, what's the load of that? How much does that timber weigh?
What was our max weight?
Okay, hang on. Here's AB. Can you see this?
Yeah.
They said this is 6 feet long and the distributed load is 6 pounds per foot.
Oh, okay.
What's this equal to?
36.
36 pounds.
Yeah, 36
right?
pounds. Yeah.
Because it's 6 pounds per foot. Every foot is 6 pounds. 6 times 6 is 36. This timber beam weighs 36 pounds.
Okay.
Okay.
Yeah.
So in the real world, the way we do this is we do this. Here's AB. We put, because it's a 2-force member, we locate all the load on the ends. So if it's 36 pounds, we put 18 pounds here and 18 pounds here. When you spread this, if you spread it over area, it's called tributary area. Okay, think of a huge skyscraper. And it's built on 4 piles, vertical piles on each corner of the building. Can you all picture a huge skyscraper and it's up in the air and it's on 4 posts? Can everybody picture that? How much weight? What's the load in each post? How do you calculate that? Dave.
Dave had a chem quiz. He had to go.
Oh. David LR. He maybe had to leave too. Edgar?
Yes.
So a building weighs 1 zillion pounds. If 4 posts are holding it up, how much weight is 1 post holding?
1/4 of the zillion.
That's right.
Thingy.
Okay. So in this problem right here, this beam is holding 36 pounds, but where it's connected is on the ends. So half of the load goes to A and half of the load goes to B. So if we were to draw this free body diagram, it already had 1,000 pounds here, 2,000 pounds here, 2,000 pounds here. It had 1,000 pounds here. In addition, it has another 18 pounds here, 18 pounds here, 18 pounds here, 18 pounds here, 18 pounds here. Does everybody get it? The load of the members always go on the connections. But if you notice, and Jason, I'm going to give you this problem. Notice, compare 18 pounds to 1,000 pounds. Does the weight have any bearing? The weight of the members, does it have any bearing?
I mean, what do you mean, does it have bearing? Yeah, it seems like this would factor into our load.
Yeah, but look at how tiny it is. 18 pounds versus 1,000 pounds.
No.
And then when I add a factor of safety, a 2, 3, 4, a 5, this is pretty meaningless. Okay.
So these are all, if I can ask a question, these are all still 2 force members.
Correct.
That's interesting.
Trusses are considered 2 force members, even though if you take the weight of the member as a distributed load, the distributed load gets applied at the end, so it's still considered a 2 force member.
But that's kind of a like a mental model. That's sort of a method of interpretation. We could also, as we've been doing so far in the class, apply that as a centered load of 36 pounds.
Yes, but that's not how that's done in engineering. We always go to the ends. Like, for instance, if you have a floor and you have all this stuff on the floor, in the end, this is what's holding up the floor. All this weight, W, is distributed versus, this is called tributary area. You're going to learn it in your junior level classes. I'm interested in introducing a term that's not used in statics yet. You're not going to see it until your junior level. But tributary area is when you take the whole weight, and what you're doing is you're taking the area and you're dividing it up into 4 because there are 4 connections, and you're saying that the weight in this area is concentrated here, the weight in this area is concentrated here, the weight in this is concentrated here, and the weight in here is concentrated here. And that's how you do all building designs, because all the weight on a floor of a building is brought to the columns.
Sure enough.
So think about this. The top floor of a building, right? Let's say the roof. The roof probably weighs more. The roof weighs more probably than the stuff in the top floor if it's an office with desks and stuff. If you think of tributary area, the amount of area of the roof is you divide it by 4, take the weight divided by 4, and it goes in those pillars on the corner. But in an earthquake, if that floor collapses on the next, and the next floor collapses on the next, and the next, you have to make sure that every floor, as you go down, the pillars hold all the weight above it. Otherwise, it's going to be a stack of cards flopping down.
Yeah.
Okay. Okay. I'm going to end class now. Hey, Jason, could you stay on?
Yes.
Thanks. Okay, everybody. I'll see you soon. And I'm going to stop the recording wherever it happens to be.